Okay, in this video we're going to take a look at dielectrics. And a dielectric is simply an insulating material which is sandwiched between the two electrodes. And in my diagram here, I've used this yellow box to represent the dielectric material. Now, the dielectric material actually serves two purposes. The first purpose served by the dielectric material is that it provides structure to the electrodes. And what we mean by that is if we say this is the positive plate and this is the negative plate, these two electrodes are going to be attracted towards each other because there's that net positive charge and then that net negative charge. And since the opposite charges attract each other, these plates want to get squeezed together. So the dielectric material prevents the spacing of the plates from changing. The second purpose for the dielectric material is that it increases capacitance by decreasing the electric field in the plates. And that's what we're going to look at now. So in between the plates of the capacitor in this dielectric material, we've got the molecules of the dielectric. And when there's an electric field present due to these plates being charged, the electric field is going to point in that direction. So this is the electric field due to the plates. Now, these charges, these molecules that are in the presence of this electric field become polarized. Now, they don't move around, but the atoms bulge. The electrons are being attracted towards the positive plate, and the nucleus is being attracted towards the negative plate. And so what we end up with is a net negative charge on one side and a net positive charge on the other side because it's been polarized. Now, what do we know about the electric field then that's in between this polarized molecule? Well, the electric field is going to go from positive to negative. So it's actually pointing in the opposite direction of the electric field due to the plate itself. So the net effect is to do this. If we make a head to tail diagram, right? So this is the original electric field. Then we put a dielectric material in between. The molecules polarize, creating an electric field in the opposite direction. Then that's going to mean that the electric field, the net electric field, which is in blue, is less than the original electric field. So I'll just call it E net is less than E naught, the original electric field, as though this were a vacuum. And that's how the dielectric is able to do that. Now, the material itself, we said it's just got to be an insulating material, and there are many different types of dielectric materials. It could be a piece of paper, it could be air, oil, styrofoam. It can be lots of different things. Now, our goal here with the rest of this video is to show you where this equation comes from. Because when we have a dielectric material, it changes our equations just a little bit. But it's just a little bit. Okay, so the capacitance, if you have a dielectric material, is going to be equal to kappa, which is the dielectric constant, times the capacitance as though it were a vacuum in between the two plates. So you can see it's just a small change, which is really nice because it's very easy to figure out what the new capacitance is if you happen to know what the dielectric constant is. You don't have to be able to prove this, but this is the theory part of the class. This is the part where we try to understand the mechanics behind the end result of our equations. So let's go ahead and see if we could figure out how you end up with this particular expression. And to do that, we're going to start with our definition of capacitance, which is C is equal to Q over delta V. And at this point in time, this is just representing a generic, general situation. And so delta V is just going to be rewritten as E times D, and this E is just a generic electric field. Now, that electric field, E, under normal circumstances, everything up to this point in time, we said was E0. There was no change in the electric field because we had no dielectric. But we no longer want to use E0, we want to use some new electric field because we now have that dielectric material in there. So E0 is now going to become, I'll call it E nu. E sub n for E nu. And how do we get E nu? Well, to do that, we're going to look at the definition for the dielectric constant. And the dielectric constant is kappa, and kappa is kind of curvy compared to a K, which tends to be straight lines. You're going to have to figure out how to write that one for yourself, by hand. But anyways, kappa is defined by the electric field before you have a dielectric constant, or the electric field within the vacuum, divided by the new electric field that you get after you place your dielectric. So we're going to solve this for E nu, and E nu is just equal to E in a vacuum over kappa. And so now we'll go ahead and substitute this back in, and we have delta V is equal to E nu times D. And so we have delta V is equal to E of a vacuum over kappa times D, but E times D we know as delta V. Okay, so this is delta V. But because it's delta V based on the electric field of a vacuum, we're going to call it delta V naught. And so what we have is delta V is equal to delta V naught over kappa. And now we'll substitute that back into the original expression we started with, and we're going to get C is equal to Q over delta V naught over kappa. Okay, now, if we have this delta V naught right here, that implies that this is the charge due to that delta V naught. Okay, so before we place our dielectric material into the space between the parallel plates, this delta V naught would create a Q naught. Okay, so we're going to get C is equal to, now kappa is going to go into the numerator, and we get kappa Q naught over delta V naught, and the Q naught over delta V naught is just C naught. So we get kappa times C naught, which was the expression that we were looking for. Okay, now just remember, you don't have to reproduce this in any way. What's most important for the exam, at least, is that you understand that the new capacitance is just the old capacitance when it was a vacuum multiplied by the dielectric constant. But it's always a good idea to try to understand where things come from, because in physics nothing's made up. You know that by now. It's one thing is built off of another thing, and we've done that a lot throughout the past year and a half or so. All right, now there is one more thing that I need to mention here about capacitors, and that is going to be the dielectric strength. And the dielectric strength just describes the potential which causes the dielectric material to break down. Now, what do we mean by break down? Well, that means that it becomes ionized, and or you might say a conducting path. You create a conducting path through the dielectric material. So remember, it goes back to this, that the molecules are polarized, so you have a positive end and a negative end, and the stronger the electric field is, in this case we would have an electric field, an external electric field pointing that way, and the internal electric field is pointing this way. But the stronger this electric field is, the more this molecule is going to polarize, the more elongated it becomes. But eventually this electric field becomes so strong that you literally rip electrons off of the molecule, and when that happens it becomes ionized. And now we have a conducting path through the material itself, and you have reached the breakdown, or you've exceeded the dielectric strength. Now, just as a couple of quick examples, air has a dielectric strength of 3 times 10 to the 6th volts per meter. I think it's something like 10,000 volts per inch. You might recognize it as that, 10,000 volts per inch. Paper, it has a dielectric strength of 16 times 10 to the 6th volts per meter. Okay, so it does quite a bit better than air. Okay, so this concludes our videos on capacitance.